Friends, welcome to the 33rd lecture of the course Advanced Steel Design. In this lecture, we are going to do some numerical examples to determine critical buckling load. We are going to use Matlab programs for doing this. Okay. So, let us first see the basis of doing this analysis. Friends, one of the basic assumptions which we made to obtain the buckling load of a structural system is the deformation is sufficiently small compared to its initial condition, that is, it undergoes very small deformation, and hence critical buckling load can be estimated using linear theory. Okay. Furthermore, friends, it is also important that buckling loads are estimated under the assumption that structures only transfer axial forces. In case they encounter transverse loads, then these loads will cause additional moments, okay, which will alter the stiffness significantly. Okay. Therefore, in such situation, one must use continuous PM interaction curve to estimate the buckling load. We must remember this. So, we are under the assumption the structure will undergo only or will encounter only axial forces. Okay. Now, let us see what is the basis fundamental logic to obtain the buckling load. Friends, we already said we are taking a basic module, okay. We are neglecting the axial deformations. Okay. Therefore, joint loads related to the unrestrained joint displacements are set to 0. You may be wondering, how do you identify an unrestrained joint displacement? We will give some examples. Let us say I take a 3-span continuous beam like this. Okay. Let me mark the unrestrained displacements for all the type of supports first. So, if it is a roller support, the roller can undergo rotation, but roller cannot undergo vertical displacement. So, I will make a table unrestrained and restrained. Okay. Let me call this as theta and this as del V. So, I should have a table unrestrained is 1, which is theta, and restrained is 1, which is del V. If I have a hinged support, this can undergo rotation, but again vertical displacement is restrained. So, 1 rotation unrestrained, 1 vertical displacement restrained. If you have a fixed support, rotation as well as restraints are. So, this 0, this is 2, 1 is theta, 1 is del. So, these are unrestrained displacements of varieties of supports. Learning this, we can now mark the unrestrained displacements in green. So, as theta 1, theta 2, and restrained degrees of freedom in red, theta 3, del 4, del 5, del 6, theta 7, del 8 by neglecting axial deformation. Okay. I can say this beam has got unrestrained joint displacements as 2, which is theta 1 and theta 2. Restrained displacements are 1, 2, 3, 4, 5, 6, which is theta 3, del 4 and so on. Okay. So, what we are now saying is unrestrained joint displacements are set to 0. So, mathematically the joint load unrestrained should be set to 0. Okay. We know for a given matrix K, if I partition this matrix as unrestrained, 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 unrestrained. So, this is KUU, this is KUR, this is KRU, this is KRR. We also know the joint load can also be partitioned as JLU and JLR. U stands for unrestrained. Okay. And the displacements can also be partitioned, unrestrained displacements and restrained displacements. Restrained displacements anyway will be equal to 0. Okay. We have an equation now. Force is stiffness multiplied by displacement. Is it not? So, we already said this should be set to 0. So, look at this equation now. This equation left hand side is 0, which implies the fact now this implies a fact that either del u must be 0 or KUU should be set to 0. Now, friends, you please see del u cannot be 0, it undergoes displacement, isn't it? Because unrestrained joint displacements are not 0. So, the non-trivial solution could be determinant of this KUU matrix should be set to 0. Okay. The equation 2 in stability analysis is called, not stability, I will say buckling analysis, is called characteristic determinant. Okay. Now, when you expand the determinant, to uptime, the buckling failure condition. Okay. Friends, we should also remember, if the axial load is lesser than the critical buckling load, that is, if axial load is lesser than critical buckling load, then the joint displacements of unrestrained joints will be 0, because for buckling failure you have to impose this displacement. Hence, determinant KUU will be positive, which corresponds to a stable condition. On the other hand, if the applied load exceeds buckling load, critical buckling load, this will refer to unstable condition, because we already said buckling is a mode of consequence of instability. So, in this case KUU determinant will be negative. Okay. That is an important point which we have to remember. Furthermore, friends, in a structural system, comprising more than one member, under axial load, then one need to establish a relationship between the axial load and the buckling load. This relationship is referred as phi I, which we have used in the derivation. Okay. Therefore, the critical buckling load can be given by the relationship PCR is phi I of pi square EI by Li square. Okay. So, if I know phi, I know E, I know cross sectional moment of inertia, I know the length of the member, I can find the critical buckling load. And if PA is lesser than PCR, applied load, we do not have to bother. If PA exceeds PCR, we can say it is failing by buckling, which is causing instability. Okay. So, with this background, let us start doing a numerical example of estimating the critical load. We will say this example 1. So, on the screen you see a column subjected to axial compressive load. The degrees of freedom are marked. So, unrestrained degrees are marked in green, that is displacements. Okay, displacements. Displacements include both rotation and translation, remember that. Okay, are marked in green color, and restrained displacements are marked in red color. So, now we can see very well here, this particular problem has got two unrestrained degrees displacements, that is theta 1 and del 2, and this has got 4 restrained degrees, namely theta 3, del 4, phi and 6. Suppose if we neglect axial deformation, then restrained degree will be 3, which will be theta 3, del 4 and del phi, because this will also become del phi, this will also become del phi. I am neglecting axial deformation. Okay. So, now we have chosen jth end at here, which is marked as A, and this is kth end, which is B at A, and kth end at B. So, this may xm and ym. Okay. Now, I can write the stiffness matrix for stability functions for this particular problem. Okay. We can recollect that equation which we wrote. So, the stability function, which will be EI times of let us mark the labels of this problem. So, rotation at J, so label is going to be rotation at j, then rotation at k, then translation along positive m, positive y at j, translation along positive y at k. So, 1, 3, 2, 4 are the labels. How do we do that? I repeat again. Rotation at jth end, rotation at kth end, translation at jth end along positive y, translation at kth end along positive y. That is standard, no? See, look at the fixed beam. This is xm, this is ym, theta p, theta q, del r and del s, is it not? So, p corresponds to rotation at jth end, q corresponds to rotation at kth end, r corresponds to translation at jth end along positive y, and s is at the kth end. So, same logic here. So, let me write down this matrix. We already know this is R by L, this is C R by L, this is 1 plus C of R by L, this is minus of this. In the next column, I just interchange this. So, this is R by L, this is C by L, and sum of these two, this is R C by L. So, 1 plus C R by L minus 1 plus C R by L, and the third column sum of these two by L. So, 1 plus C R by L, sum of these two 1 plus C R by L, then sum of these two by L, but I have to use by L square, right? This is L square, by L square again. So, this is L, sorry, this is L square, this is L square, because it is sum of these two by L, is it not? Again this is L square, sum of these two by L. So, now this particular value K33 will be sum of these two read by L. So, let me write that. So, twice of 1 plus C R by L cube, and I also say T, translation function, is it not? So, minus 2 R T 1 plus C by L cube. Fourth column is minus of third. So, minus of 1 plus C R by L square minus of 1 plus C R by L square minus of 2 R T 1 plus C L cube 2 R T 1 plus C L cube. So, this is what my matrix is. Let me enter the labels. We already marked the labels 1, 3, 2, 4. So, 1, 3, 2, 4. Okay. Now, friends, please note this problem has 2 unrestrained degrees, is it not? So, therefore, I must partition this matrix at 2 by 2 to get my KUU. So, let me partition this matrix at 2 by 2, and this becomes my KUU, is it not? So, I can now write KUU as R by L, CR by L, sorry, 1, 2, sorry. So, not partitioning, I think we can pick up the first and second. So, I must pick up K11, K12 and then K21 and K22. So, let me write KUU as K11, K12 1 plus C R by L square, then K21 1 plus C R by L square, then K22 which is 2 times of RT 1 plus C by L cube. Am I right? So, I have KUU now. So, let me copy this and put it here. I have KUU. Okay, let me this is my KU matrix. Okay. As we just now discussed, I must set determinant of this to 0. So, setting determinant of KUU to 0. So, if I do that, so it is going to be R by L into 2 RT 1 plus C by L cube minus 1 plus C R by L square, the whole square, is it not? Should be set to 0. Simplifying. You can simplify this very easily, because you know L4 here, okay, 1 plus C into R, 1 plus C into R here on the left hand side. So, if I say R by L square of 2RT 1 plus C is equal to 1 plus C into R, 1 plus C into R by L4, okay, L4 goes away, 1 plus C goes away, R goes away, okay. And one more R goes away. So, I can now say 2T is equal to 1 plus C, or 2T minus C will be 1. This is my control equation. These are all stability functions, T, C and R are stability functions, friends, which we derived in the previous lectures. Okay. Under axial compression, axial tension, we have these values. So, the equation 1 on the screen is called characteristic equation. Which is 2T minus C is 1 is called characteristic equation. So, now for different values of phi I, we have the stability charts, is it not? Which indicates R, C and T values. So, what I should do? I should go to the table, choose phi I value which satisfies the characteristic equation. Okay. I will show you typically how the stability chart looks like. Give me a minute. Friends, I will just enlarge this. So, typical stability chart, friends. For different values of phi, okay, minus indicates tension and positive indicates compression. Okay, it goes to 0, the 0 value is here, okay, then it goes positive. So, positive compression. So, it is varying from minus 10 phi I value to plus 4, okay, we can see that plus 4, right. So, the first column refers to R, T and C. So, these are the values. So, what I should do for this control equation, to be satisfied, I must choose a phi value. It is very difficult, no? It is very difficult to undergo or scan all the entire table to satisfy this equation. So, to solve this problem, we use a Matlab program. So, I will show you. So, we are now using a Matlab program. The program is available in the textbook referred in this course. You can download the program easily. Matlab support is also extended for NPTEL students through IIT Madras link. You can also undergo free tutorials to learn Matlab. Program is given to you and it does not require a sophisticated laptop or a desktop to run a Matlab software. Okay, a normal laptop should be able to run the problem what I am discussing about. Matlab has got many facilities which requires an high-end computational facility. However, the problem what I am discussing now can be run on an ordinary conventional laptop. Okay, do not worry about that. Okay. So, now I will show you the Matlab program. So, friends, what you see on the screen is the Matlab program. Okay. So, this is a program written for compression. You can say from 0.01 to 4, we saw the value just now on the table, and for tension it plots up to 10, tension is minus, okay, there is minus, right, and then for 0 also we have plotted, okay. So, program, it gives you a stability functions R, C and T. This is an equation but we already have derived, you know this, so we can easily, and chart is also prepared. Then further, friends, we have a control equation which is the characteristic equation for this problem, 2T minus C is 1. So, a program is written to equate and find a specific phi value from the output file which is generated from you, okay, to satisfy this equation. So, this program is now run. So, it gives me the phi value, please see on the screen, 0.25. It also shows me the chart for your learning. This is my R value variation and this is my C variation with respect to phi, and this is variation of T with respect to phi, okay, it is a chart. So, it gives me, after searching in the table or the chart, gives me a phi value as 0.25, okay. So, now I got phi value as 0.25 from the Matlab. So, I will go to the screen now. So, I have got phi value as 0.25. Now, how do I get the buckling block? That is the question, is it not? So, now for phi value of 0.25, from the chart or table you can refer, R will be 3.6598, T will be 0.7854 and C is 0.5708, which satisfies the characteristic equation. So, now what I do, I substitute PCR as phi I of pi square EI by Li square, okay, where phi is 0.25. If we know the material constant, if we know the second moment of area or moment of inertia of the cross section, if I know the length of the member, I can find the Euler's critical load. So, the problem is very simple, friends. Stability functions help you to obtain the Euler's critical load, which will going to help you to estimate the buckling load. Okay? So, program is given, derivations are clear, application is being done, and I think it is very easy for us to practice more number of problems, is it not? Let us do one more problem. So, example 2. Okay, we will do one more problem. So, this is example 2 where one member is having 2I, other member has moment of inertia as I. A, B and C are the nodes. Okay. As the length of the member is same, I can interpret this angle as 45 degrees. Okay. Right. Now, I can also find at node B, if I have a load P applied here, I can find the component of this load, which I am going to call as PBC, and the component of this load, which I am going to call as PAB or PBA, as 0.707 P. So, the angle is 45 degrees, right? This angle is 90 and this angle is 45. So, now I can say the axial load on the member AB is 0.707 P compressive. The axial load on the member BC is 0.707 P compressive. Now, there are two members sharing this load P. So, we have to carefully form the characteristic equation. Okay. Now, let us mark the unrestrained degrees. One can see here on the screen theta 1 and theta 2 are the rotations which are unrestrained, remaining all are restrained, and look at del 4 same both places, indicating we are neglecting axial deformation. Similarly, del phi and del phi neglects axial deformation along the member BC. Okay. So, I can say this member has unrestrained degrees 2, which are theta 1 and theta 2, restrained degrees as 1, 2, 3, 1, 3, 4, 5, okay, 6 and 7. So, 5 which are del 3, del 4, del 5, theta 6 and del 7. So, the total kinematic degree of freedom is 7, neglecting axial deformation, restrained is 5, unrestrained is 2. Okay. As usual, I have to now derive the stiffness matrix using rotational stability functions for the member AB and for the member BC. Okay. So, for the member AB, I will make a table. For the member J and K and N, L, I and labels. Let us say for the member AB, I am going to say the jth end is at B and kth end is at A. So, that is here. So, this is my xm and this is my ym for the member AB. Okay. Length of the member AB is L, and moment of inertia is 2I, is it not? Let me mark the labels for the member AB. So, rotation at J, rotation at K, displacement along positive Y at J and at K, is it not? So, rotation is 1, rotation is then 2, then 5 and 3. So, the labels should be, strictly speaking, 1, 2, 5 and 3. So, let us say the labels are 1, 2, 5 and 3. Now, for the member BC, okay, for the member BC, we will take the jth end at B and this at C. So, the jth end is here. So, this becomes my xm and ym for the member BC. Okay, the labels are going to be 1, 6, 4 and 7, isn't it? So, labels are 1, 6, okay, 4 and 7, right. The length of the member is again L, but the moment of inertia is only I. So, I do not think there is any confusion for you people to write this table. Once this table is done, let us now write the matrix for the member AB and the matrix for the member BC. Okay, 4 by 4. So, E into 2I for the member AB, right. So, I should say it is R1 by L, C1 R1 by L, 1 plus C1 of R1 by L square minus 1 plus C1 R1 by L square. So, then across this is C1 R1 by L, this is R1 by L, this is 1 plus C1 of R1 by L, 1 plus C1 of R1 by L. Then we add these two and divide by L. So, 1 plus C1 R1 by L square, 1 plus C1 R1 by L square, that is adding these two by L, then adding these two by L but a T along with that. So, that is going to be 2 T1 R1 1 plus C1 by L cube, right, minus 2 T1 R1 1 plus C1 by L cube. The fourth column is negative of 3. So, minus of 1 plus C1 R1 by L square minus of 1 plus C1 R1 by L square minus of 2 T1 R1 1 plus C1 by L cube plus of 2 T1 R1 1 plus C1 by L cube, right. Let us mark the labels. For the member AB is 1, 2, 5, 3, okay. 1, 2, 5 and 3. Similarly, here 1, 2, 5 and 3. Then for the member BC, let me do it to the next page. K BC R2 by L2, L, that is the length of the member, C2 R2 by L, 1 plus C2 R2 by L minus 1 plus C2, then it is crossed. So, C2 R2 by L, R2 by L, 1 plus C2 R2 by L minus of, then sum of these two by L. This is L square, right? There will be L square here. The previous case also L square, right? That is right. L square here. Okay. Then sum of these two by L. Then sum of these two by L again. So, 2T2 R2 1 plus C2 by L cube minus of 2T2 R2 1 plus C2 by L cube. The fourth column is minus of this. Okay. We also know the labels of this is 1, 6, 4, 7. So, let us enter the labels 1, 6, 4, 7. Now, friends, let us form KUU. Okay, let us form KUU. How many understand degrees are there? We have got 2 understand degrees in this problem. See here 1 and 2. So, I must get EI common 1 and 2. So, I must find K11. Let us look at this. K11 is this, I am just indicating with maybe the pink color. K11 is this from here. So, K11, okay, plus the other one is K1. Okay. So, now please note there is a 2 multiplier here. So, 2 R1 by L1, 2 R1 by L, L1 is the same. Okay. So, then for the second member it is R2 by L. Okay. Then let us go to 1, 2 from here. 1, 2 is this value. So, 2 C1 R1 by L, right? 2 C1 R1 by L. Why this 2 has come? This 2 has come because of this. This 2 has come because of this. Okay. Now, I must get 2 1. Go here. 2 1 is this value. Okay. So, 2 C1 R1 by L, correct. Then let us go to 2 2. 2 2 is this value. We also have 2 2 here. Oh. We also have 2 2 here. No, we do not have it. Okay, only this. So, 2 2 is R1 by L. There is a 2 here. So, I should say 2 R1 by L. Okay, friends, we have got KUU matrix now. Now, I must set this determinant of KUU to 0. Okay. So, this diagonal multiply minus this diagonal and set it to 0. Okay. So, I should say 2 R1 plus R2 by L into 2 R1 by L minus 2 C1 R1 by L, the whole square should be 0. Am I right? Okay. This is what I must get. Set it to 0. When I set this to 0 and expand and simplify, we get the characteristic equation as 2R1 of 1 minus C1 square plus R2 is 0. Okay. This is my characteristic equation. Further, we know PCR1 is PCR2, which is PCR of 0.707, isn't it? Well, that is the load which is being applied. Therefore, friends, we have one more relationship. Phi 1 will be P times of 0.707 pi square E to I by L square. Phi 2 will be P of 0.707 by pi square E I by L square. So, comparing these two equations, we can now also say two phi 1 is phi 2, you can see easily from here. Okay, 2 phi 1 will be phi 2, right. So, I have to satisfy two equations while selecting phi. So, I must find phi 1 and phi 2, because phi 1 and phi 2 will be helpful to get P, okay, and the characteristic equation should be satisfied. So, I can refer to the chart or the table and try to get. So, I am going to use Matlab again. So, using Matlab, so again the same plot, but I am going to show you the control equation. The control equation what we had is 2R1 1 minus C1 square, okay, plus R2 is 0, isn't it? This is the control equation here, okay. So, we have developed this control equation, apply this and wrote an algorithm, and then we run this program. So, forget about these plots, we get phi 1 as 1.01 and phi 2 as 2.02, okay. So, I will write it here, I will close this, minimize this, these are charts being plotted and minimize this. So, now I can write phi 1 is 1.01 and phi 2 is 2.02. For these values, we got R1 as 2.4493, T1 as 0.0124 and C1 as 1.0101 and R2 as 0.1120, T2 as 1.7148 and C2 as 31.6264. Okay. So, now I have got P critical is phi 1 times of pi square E of 2I by 0.707 of L square. So, phi 1 I already have, which is 1.01. So, if I know E, if I know I, if I know L, I can find P. Okay. So, friends, in this lecture, we learnt the difference between buckling and stability analysis. We also learnt how to set the characteristic equation to solve a buckling problem. for a frame subject to axial loads. So, we said that set the KUU determinant to 0 for a non-trivial solution and try to get the control equation and then choose the phi values from the chart or the table and try to find the phi. Once I know the phi value, I can find P critical. Okay? So, I wish you should do more examples to solve more problems and try to learn more about this. So, friends, stability analysis is not difficult, it is easy. Please practice more problems and use the Matlab program given, and also this book will be very helpful for you which is being used as a reference. So, please refer to this book, Design Aids of Offshore Structures, Topside Platforms Under Special Loads, which has got the stability charts and the table and also the Matlab program. Okay, this is a CRC press release. This book is available in public domain. Please access to this book through your institute library, subscribe this to your library, recommend this to your research scholars and friends and faculty colleagues, and I hope you will find very useful contributions from this book for your additional learning on this course. Thank you very much and have a good day.